Good morning, everybody. Welcome to this session on dynamic mode decomposition. My name is Andre Weiner. I'm a postdoc at the University of Braunschweig. And yeah, so a couple of words up front, maybe. So this is not a formal talk, it's just a training session. So please feel free to interrupt me anytime. Feel free to ask, okay?
Do you plan to use the microphone?
The microphone?
Yes.
Yes. So there's somebody here who will pass around the microphone. But
it's a bit quiet. You can project a bit more. I can't hear you back.
Okay. I have a microphone, but I have a microphone, but this is I think for the online audience. So I'm not sure if this would work. Maybe would it be possible if you just come up here to the front row? This is a simpler solution, maybe. Yeah, I was thinking about that too, but you know, it's a packed room and not so much volume, so. Okay. All right. Yeah, so please feel free, just now, to interrupt me anytime to ask questions about, you know, theory of dynamic mode decomposition, like practical questions, also related to code. So I'm going to show you some Python code, mostly some OpenFOAM case setups, function objects mainly. So if you have any questions about that, feel free to ask and to interrupt me anytime, right? The same is, of course, true for the audience. So the online audience, I try to keep an eye on the Zoom chat, and yeah, I think it works. So I can already see that you wrote something in the chat. All right, okay, then let's get started. What I'm going to go through today is, first I will show you an example simulation that I want to use for this demonstration. It's actually from the OpenFOAM tutorial collection, and the setup is called surface mounted cube. Does anybody of you, maybe a quick show of hands, know the surface mounted cube tutorial? Okay, Gavin, that's good. Okay, two. Okay, then you know it very well, maybe. So if there are any, like, you know, IDDS related questions, you can ask Gavin. All right. Yeah, so I chose this particular tutorial because very often you see for the introduction of POD, dynamic mode decomposition, DMD, you see something like a laminar flow past a 2D cylinder, right? And then usually the question is, okay, what do I actually learn from these like awkward looking dynamic modes? You know, what do I understand that I couldn't understand before? Because for a simple two-dimensional laminar flow, usually you can just, you know, watch an animation of the video and then you have it all figured out, right? So this case is, it has some resolved turbulence. It's a hybrid simulation, and it's three-dimensional, and it's not a cylinder, but a cube. So there are some, let's say, more complicated flow structures that you cannot simply have a look at and then understand what's going on, right? So I think this is a nice tutorial. A disadvantage is that, you know, in case you want to just try this out on your computer, you need like 40 MPI rings to run the simulation, and so most likely you will not do it during this session. Okay, and then I will give you a very short overview of DMD theory, and only that part that me personally helped a lot to understand why I get certain information from DMD. Okay, so it's not going to be like a full theory introduction. Then I also want to show you not just like how to, you know, set up the DMD in OpenFOAM and to, you know, look at the results, but I also want to, you know, show you the full workflow that I usually follow when I want to analyze coherent structures. So dynamic modes are just like one part of the workflow, but there's some information that you need prior to performing DMD, and I will also show you, you know, how you get this information. Then I will show you two applications of two ways how to perform DMD. The first one is to just load OpenFOAM data into Python and then to perform the DMD and visualization tasks in Python. And the second one will be with the native OpenFOAM DMD function object. Now there's a little problem with the last part. I can show you basically how everything is set up, but unfortunately I cannot show you the final results there because since yesterday, I don't have access anymore to the university's cluster where all the data is located. And I can show you, I think, everything that you need to know, let's say. Just some nice visualizations are left out. All right. Then, yeah, the training material, everything that I'm going to show you, the case setups, the scripts, how to run them, the Jupyter notebooks that I will show you. What else? The slides. So you find a link to these slides. You see the slides are actually available online. You find everything if you follow this GitHub link. So you will, where is it? Okay, you get to this GitHub repository where basically all the information is gathered. So you find here information how to run the simulations, the training material that I will go through, the data if you want to download some of the data to perform the analysis on your laptop, maybe somewhere during the next days. Then also the dependencies. So everything that I'm going to show you today will only work with OpenFOAM, with the latest OpenFOAM version, so 22.06. And the reason is that, there have been some small modifications in some function objects that I'm using, and also the DMD basically in every release of the past 2 years or so has undergone improvements. So it's becoming better and better every time, more performant, more stable, and so on. So also from the DMD point of view, I would also recommend to go with the latest version that is available. Okay. But yeah, so this repository should be more or less self-explanatory. If not, then also after the workshop, just feel free to open up an issue and to ask your questions. All right. So here's just a little preview of what we are going to work with. So this is now a 2D slice taken from this tutorial. And you see we have a cube that is somewhere located, more or less at the center of the domain. And then we have a flow coming from the left. We have some really nice vortex shedding on the cube surface, some really complex flow structures developing in the wake. And so just to say it again, this is actually a slice from a 3D simulation, right? It's not a 2D data. And you find basically all the information that are needed to understand the simulation setup if you follow this link to the OpenFOAM documentation. There you see a little bit more an overview of the geometry, where the cube is located. And I think this slice, what we are looking at, was basically taking about here. You see my point? Yeah. Okay. And I'm not going to do any introduction on the turbulence modeling or where this setup comes from. There's also experimental data available. You find everything actually linked here on this page. All right, now comes a little theory introduction. Luckily, we are still in the morning session, and you're all still very awake and had just had a coffee. So I think it's a perfect time to listen to some DMD theory. All right, the first concept I want to talk about is modal decomposition. Sounds a little bit strange, and I didn't know what it is actually maybe like 2 years ago, but the concept is actually very simple. So let's say you have unsteady flow, And what dynamic mode or what mode decomposition in general does, not just dynamic mode decomposition, is to take this three-dimensional unsteady flow field and decomposes it into two parts. The first one is are basically flow structures that change in space but are constant in time. And the second part is like some temporal behavior that tells you how these modes are superimposed over time. So what the mode's importance is over time. So the left one you see, the left picture you see here, this is one example of a mode for density. So this mode does not change in time, right? It's like a spatial structure. And on the right side, you see like a simple scalar signal for how the importance of this mode changes over time. This is actually not just, this is not dynamic mode decomposition, but it's proper orthogonal decomposition and similar technique, but the concept is always the same. You decompose your three-dimensional unsteady flow field into spatial structures that vary in space and are constant in time, and the temporal importance of these modes. Okay. All right, the basis for any mode decomposition technique is snapshot data. So what does it mean, snapshot data? Let's say you have your pressure field, your velocity field, right? Then you have maybe sometimes scalar quantities, sometimes vectorial quantities like velocity. And what we do in general for any mode decomposition technique is that we take the entire field of pressure, let's say, or of velocity, and we stack all the cell-centered values in case of OpenFOAM into a really, really long column vector. Okay, so for example, if you have a non-scalar quantity like velocity, you will take the x component of the velocity, stack it into the vector, and then you will take the y component, put it after that, take the z component, put it after that. So very simple example, let's say you have a field with, you have a mesh with 100 cells, and then you have the velocity, you take the velocity field to form the state vector. Maybe quick question, how long is one state vector going to be? 100 cells, velocity? Yes, 300 is the correct answer. All right, so that's what a state vector is, okay? And there is some degree of freedom how to form the state vector. You can, simply take the raw data. You can also use some physical intuition, especially if you have compressible flows, for example, on how to compose the state vector. And the second thing, what we are going to do is we're going to take all these snapshots and stack them into a very large data matrix. So let's say we have run our OpenFOAM simulation. We have written snapshots at every 0.1 seconds, and we have simulated 1 second. Then we are going to have 10 snapshots, right? And this matrix, sticking to the 100 cell mesh, then this matrix is going to be 300 by 100 matrix. Because we're getting one state vector for every time that we have written to disk. Okay, so when we have when we wrote 10 snapshots, then the matrix will have 10 columns. Yeah. Questions about that so far? Online? No, not the case. Okay. Yeah.
1 to n refers to that small n?
Yes. Yes. So let's say we have n snapshots, yeah, and we start from the first one, then n would be the indexing variable of the column.
So pressure, velocity, this matrix include pressure and velocity, or pressure or velocity?
It can actually include both, depending on how you form the state vector. Oh. So for incompressible flows, probably what you would take is the velocity vector. But you could also work with the pressure, for example. What is not, what you can do technically, but what is not really necessarily sensible, is to put the pressure and the velocity into one state vector without any normalization. Because pressure is in pascals or like kinematic pressure units, and velocity is meters per second, and you do not want to sum pascals and meters per second together. So you would probably do some, normalization, also using some physical intuition, like how you, like Bernoulli equation, for example. Okay, sure. Any other questions? Yeah. I should remember to, if I don't do, please remember me to repeat the question such that the online audience can also follow. Okay, please.
Just the definition of these indices. So if I understand, the capital N here is the number of snapshots, while the small n is the degree of freedom of the state vector, which is basically the number of computational cells, for example. Is that correct?
Okay, so the question is, if n is the number of cells of the state vector, and that's not the case. So n really indexes the snapshot. So basically, n is the variable that goes from the index that goes from 1 to capital N. So yeah, and so basically, I haven't actually any index. I do not have any index here on this slide for how many degrees of freedoms there actually are.
Okay.
That's just somewhere hidden in the X.
Yeah.
Further questions? Because this is like, if you understand this, then it's already 50% of the job. Okay, so that's, yeah.
Is it important that these snapshots be uniformly spaced from instances in time?
Yes, that's very important. Yes. I mean, you can, there are some tricks you can do afterwards if they're not uniformly spaced in time, but in general, you avoid a lot of trouble, a lot of headache if you just write them equidistantly spaced in time. Yeah, good remark. Thank you.
Just another question. What would be the advantage of putting pressure and velocity together in one state vector? So what was the point in that?
You increase the dimension. So the question is, what could be the advantage of putting like more flow variables into a long state vector? And the answer is that you increase the degrees of freedom. So you may have some information in the pressure that you do not have in the velocity in general. Like for incompressible flows, it's not worth it. But for compressible flows, you may you may have different information in density or local speed of sound than you have in just the velocity.
Okay.
Yes, and there's also another technique. You will find it in the literature as Hankel DMD, which is basically the idea that you shift your snapshots by one at a time, and then you use the shifted snapshots and stack them on top of your data matrix to increase, like, it's like, for example, imagine you have some effect that is accelerating, right? And you cannot just like from the current situation estimate what the next state is going to be. You need like, at least 2 states to know like any transient effects, let's say.
So because DMT is based on the modal frequency of the flow, right? So do you have any suggestion on the right interval? What should be a good right interval?
Yeah. So the question is if there's any rule of thumb how to determine the right interval, and I will get to that a little bit later during the training. It's a very important question. Yeah. More questions? Right. Then let's continue. Now.
Excuse me, in your last questions, you mentioned that if you increase the number of variables, it increases the degree of freedom or decreases. Can you please clarify?
I didn't fully understand the question, but I think it was the question was whether the degree of freedom increases if you use a larger state vector, and the answer is yes. Does it answer your question? Yes, you can.
Go ahead, please.
Okay. Next question is, can you use derived fields like vorticity or the Q criterion? And again, the answer is yes. And sometimes that's very sensible to do. Yes. So in general, one really nice thing about most of the dynamic mode decomposition techniques like POD and DMD is that you can just use any data. The source doesn't really matter. So it can be experimental data. It can be a combination of numerical and experimental data. Can be derived fields where you put some physical knowledge into the state. Can be anything. All right. One really essential matrix factorization for many mode decomposition techniques is the singular value decomposition. So now we take our data matrix X and we factorize it into 3 matrices, U, sigma, and V. The terminology is usually that U contains the left singular vectors, and the column vectors of U, they are also called POD modes. Okay, so we get basically 2 modal decomposition techniques for the price of 1, you could say, in the DMD. Then the sigma matrix is going to have like a diagonal non-zero submatrix with the singular values on the diagonal that tell you basically how important a certain mode is. So the column vectors, how important the column vectors of U are. And then the V vector is going to have temporal information. So the left singular vectors, the columns of the V matrix are called right singular vectors, and they will tell you if you want to reconstruct the original flow field, how much of each individual left singular vector you should use. And you can, if in the case of snapshot data, you can interpret that as the importance over time. So this is where this temporal information comes from associated with each mode. But that's only for the singular value decomposition. And one mathematical property that is important, U and V are orthonormal matrices, or unitary actually in the complex sense. Now we are getting to the DMD. The core idea of the DMD is that we take our snapshot, we take our state vector X, and then we apply a linear map to it. So we multiply it with a matrix A that maps this state by 1 time step into the future, such that we can get X n plus 1. And usually, even if you have a very high dimensional state vector, there's not going to be a unique A that works for all the pairs of snapshots. And sorry, I didn't write this down here because I condensed the slides a little bit, but M here would be now the number of cell volumes in your mesh, or of the portion of your mesh that you selected for analysis, right? So this is going to be, if you now do the computation, if you have like a 20 million cell mesh, this is going to be a gigantic matrix, but in practice, you are never going to compute it. There are like many, so the actual rank of the matrix is usually much lower if you have coherent structures, such that you can work with a similar matrix that is much, much smaller. But this is too much into the theory, and I'm not going to get into that today. All right. Now, as I mentioned, there's not going to be a unique A that works for all combinations of snapshots, right? So what you usually do is you define or compute A in the least square sense. And so you can imagine if I have a matrix X that contains every snapshot but the last one, and I have a matrix X prime that contains every snapshot starting from the second snapshot to the last, then I can basically multiply X with A, and then I get X prime. So that's the equation you see here on the left. And now if you multiply this equation from the right with the inverse of X, you get the typical definition of A in the least square sense. So you don't see that it's a least squares approximation here, but you can actually show it's the least squares in the L2 norm operator. All right, and if you, this is where the singular value decomposition comes in. you can now compute the inverse of this huge matrix X using the singular value decomposition. And now comes the little bit hairy part. This is where the decomposition actually happens. So the separation between space and time. And this is essentially done using an eigenvalue decomposition. So we compute the eigenvalue decomposition of A, which is phi, lambda, phi inverse. Okay. Lambda is going to be a diagonal matrix. Now, if we take this equation here and just map x1 by one time step into the future to get x2, we can actually replace x with its A with its eigenvalue decomposition. Okay, and then you could do the same trick with x2. So you multiply x2 with A and you get x3, right? So you multiply, this is the same as multiplying A times x1 by A again. If you plug in the eigenvalue decomposition, you see you get here in the middle, you get phi to the -1 times phi, which gives you the identity. And then you arrive at this equation here on the right. So you have eigenvectors times lambda to the power of 2 for this search snapshot times inverse of phi times the initial condition, so to say. And if you generalize this to any time snapshot n, then you get basically phi times n to the -1 times phi inverse times initial condition, initial state. Okay, and the important point here is that the phi's, they do not change over time. Only the lambda term changes over time, because only in the lambda term actually the snapshot number goes in. Okay. Yes.
What I understand from here, the phi matrix, the A matrix is never self-adjoint. So
so the question is, if the A matrix is self-adjoint, you can enforce it to be self-adjoint, but usually it's not. No.
Okay. No, unless you count with the transpose of phi instead. Okay.
Yeah.
Just a quick question: is the matrix A here is the same matrix A in the previous slides, or practically it's probably projected the POD modes, as you mentioned, like it's quite expensive to compute. So, so in that sense, like with these formulations, the matrix A is still the same expensive matrix, or this is a different reduced version.
Okay, so the question is if this A is still the same as on the previous slides, or if it's in practice like a projected version of A. And the answer is like for this, understanding the theory, it doesn't really matter. So for now, it has to be, for those equations to be valid, it has to be the full A. Yeah. All right. And okay, I already went more or less through the terminology a little bit. So phi contains the column vectors of phi. This is what you call the dynamic modes. Lambda are the eigenvalues. And usually you compute phi inverse times initial state and call that B. So, and in the DMD sense, to make some connection to the like fast Fourier transformation of scalar signals, you call that the mode amplitudes. So every row of B is going to tell you how important a certain column of the phi matrix is. So this is why it's called amplitude. Okay. Now comes the interesting part, I think, for making the connections to frequencies, and why you get a very particular property of having only one frequency connected with each DMD mode. And to figure this out, we are going to the time continuous formulation. So we are imagining now that our delta t becomes infinitely small. Is there a question? I couldn't hear anything. Could you please write it to the chat if there's any question? All right. So you move to the time continuous formulation. So what we get now is basically a system of ordinary differential equations. Yes. And you can actually solve this system of ordinary differential equations, again, using an eigenvalue decomposition of the matrix A, which is now not the same A as before, right? Before we had like the discrete A, and now we have the A that has like that is like infinitely large. And this is also why the lambda has a little like tilde sign here on top. Okay. Starting from the eigenvalue decomposition, you can multiply from the left with phi inverse. And then what you can see is that you can substitute phi inverse times x with some other variable. And then you get a simplified system of equations, dy dt equal lambda matrix times state y. And now, because lambda is a diagonal matrix, this basically decouples all the different ordinary differential equations, and you can actually solve them one by one and write down a solution of the complete system by just like resubstituting y again with the definition of y. And then you arrive at the final equation here, which is also the last theory slide actually. So you have x of t. You can now compute x at any particular at any given continuous time value t. And the one important result is that the phi actually between the time continuous and the discrete a is the same, but the lambda is connected by an exponential function. And this is why I wanted to show you this. Many times you see then in the computation of the DMD in Python, also in OpenFOAM, you see that basically you take the eigenvalues of your operator A, and then you compute the logarithm, and then you divide it by 2 pi to get the frequencies. And this comes actually from this relation here, because typically we will not know the lambda tilde, but we will know the lambda of the discrete operator, and we have to convert basically from discrete to time continuous. Okay, sorry, I have one more slide. And this is basically about the eigenvalues and their complex nature. So, not everybody uses complex values every day. So I just thought this would be sensible to put this here. So if you say lambda is a complex eigenvalue with a real part A and the complex part B, and you take the exponential of this, what we have in the solution of the DMD, then you can actually factor this out, factor the real part out, and get like e to the power of the real part times t, and then here you have something periodic. And okay, from this periodic part, so from the complex part of the eigenvalue, we can extract the frequency information. And from the real part, we get some kind of growth information, growth or decay information. So because if you have e to the power of something larger than 1, it's going to explode. If you have e to the power of something smaller than 1, then it's going to vanish as you go forward in time. All right. That's really all of the theory parts. I hope it was okay, not too painful. Okay, as I mentioned, there are many more details on how to actually compute a DMD and how to perform certain optimization steps to get good and reproducible results. But I'm not going to talk about that today. All right, let's get to the practical part. So there has been already the very important question on how to figure out, like, how many snapshots do I need, the time sequence, the length of the time sequence, the spacing, or the delta t. And what I usually do is I perform like an initial simulation where I only have, like a relatively short amount of physical time, just to have enough of maybe like one integral time scale. So it doesn't have to be like very precise frequency information that comes out of the signal, but just something to get a rough estimate. Of course, if you have more, it's better, but we don't want to waste computational resources and run like super long simulations. And maybe I go back to the case setup. And what I usually do to get the necessary information is I use function objects. You find them here in the first case called, sorry, that's the wrong one. Full case is the one for the preliminary analysis. And everything is contained inside this control dict. So what we have here is, first of all, a field average function object that computes, first of all, the temporal mean, but also fluctuations for different fields. And this is important to know basically where things in the flow are happening, right? This gives you a good intuition. For example, if you want to place some probes later on, where to place these probes, because you want to have them in places of high variance, or places in general that are of interest to you, of course. And here I also write out the surface values of the pressure on the cube. It's not so important for this setup here. But what is more important is the forces function object. So we are actually measuring the forces acting on the cube. And typically it doesn't have to be forces, but typically we'll have some kind of integral information that is of importance to you. And I would also record this. And then what I also have here is like a probes function object, where I selected some probes actually based on the description here. If you scroll down a little bit, you already have a good picture of how the flow is going to look like. And what I did is basically I placed some probes here upstream of the cube. I placed some probes here in the wake. I placed some probes besides the cube, and I placed some probes on top of the cube, like slightly above the cube, because this might be positions that are interesting, and some are, just for control, let's say, that nothing awkward is happening. Oh. Okay, so these are the probes and the forces. And why do I need these function objects? Because, well, you can sample them every time step, every numerical time step, and you're not going to fill up your disk space. So this is why probes and forces are a good tool to get a first idea of the frequency content of your flow. So what I do then is I go usually to Python, and then I analyze flow forces and velocity probes here in Python. And I will also, if you have questions about the Python code, just let me know. I would just comment on some things that I consider important. You can actually read, like, for example, the coefficients, the force coefficients in a line of Python code using the pandas library, or more precisely, the read CSV function from the pandas library. And you get basically an object called the data frame that contains the important information, so time and the coefficient values in X, Y, Z. And this is now just a little bit of plotting. You see there's quite some scatter in the data, and what the blue curves are, sorry, the solid black lines are basically filtered versions of the signal. So the scatter is basically the force measured at every time step, and the solid black lines are filtered versions of that. Okay. And so before performing an FFT or a p-Welch, so in this case, I would also recommend to actually filter the coefficients to take away some of the noise. And this is what you get. You see here the power spectral density. And, you know, the blue dashed lines is what you would get without the filtering first. So you get a lot of noise at higher frequencies. And we do not want to, yeah, it makes the analysis a little bit more tricky. If you look at the peaks, you find here a peak at 0.1 Hertz, and you find a peak in the, let me scroll up a little bit more. Okay, so green is essentially the force coefficient for the side force. So if you are in a car, this is the force that makes it hard to keep the steering wheel straight. And orange is the force, the drag force. And you see a typical behavior of a vortex shedding. So we get in the side force a frequency of 0.1 Hertz. And then in the drag force, we get a peak at twice this frequency. But what is more important actually from this spectrum is to see basically where are high frequency content that could be interesting later on. And you see in the Y signal, we have some peaks here at about 1, maybe 1.5, maybe 2, going up to maybe, I don't know, 4 or so, 4 Hertz. And you see then it's decaying at about 10. And this gives you a pretty good idea for how to select the time step when later on sampling snapshots. Because if you keep the Nyquist theorem in mind, then you know like a good sampling frequency would be probably 20 Hertz. You can also go lower, but then you will, you know, cut off some of the high frequency content. Any questions about that so far? Yeah.
Is it possible that we utilize less snapshots and kind of make use of the this dynamical system to predict further frequencies?
Okay.
Dynamics that were not really captured in the data that we used to construct the DMD model.
Okay, the question is if you can, if you have an undersampled flow, if you can use DMD to make up for this missing sampling rate.
Yeah.
Yeah, and the short answer is no, because what you will get so it's not completely worthless, let's say, if you have like an undersampled flow, because the dominant modes at low frequencies, you will capture them nonetheless. But what usually happens is that the high frequency modes, they will be kind of flipped over at the maximum theoretical frequency, and you get some kind of aliasing effect also in the DMD. So you will find similar modes, but they are the wrong frequency. And so I'm not sure like how one could make up for that. How is DMD different from FFT? That's a very good question. So FFT essentially works with a scalar signal, right? And DMD works with the entire field. So DMD gives you for the entire flow field modes that are associated with a unique frequency. Like every mode is associated with a unique frequency. So it's like a mixture between proportional decomposition and FFT. Yeah, spatial information, one could say, yes. All right. Then I have some probes here that are less noisy and nicer to analyze. And you can, you can repeat the same process. You find, for example, here peak in the, this is actually a probe taking from above the cylinder, and you find a peak at 1.6 hertz. Now, one interesting thing that you also cannot figure out from the FFT or p-Welch is you now see this this frequency peak there, but you do not know like what causes it, right? You do not know like which kind of flow structures, vortices are leading to this frequency. You just see that it's there if you take like one single location. And I will show you in a moment how the DMD actually can show you which spatial structures are associated with this frequency. Okay. Now I will first of all show you how we can perform DMD in Python. And one thing that I should mention here is actually what I did is I sampled. Question. Yes.
The analysis that you are showing is for this surface mounted cube.
Yes.
It's stationary, right? What if your cylinder is vibrating with the flow, like flow induced vibrations? So in this case, how it would be different compared to this one, like analyzing snapshots and how many length scales you should take?
So if you really have vibrations in the sense that you have like fluid structure interactions, then the entire process will become much more complicated. And I'm actually not sure how to do that. So one would probably have to map the flow field into some reference frame that is moving with the surface, something like that. But I'm not sure, like it would be much more complicated.
Okay.
It's not clear to me because when we say fluid structure interaction system, the resultant weight is what comes out of the coupled interaction between the fluid and the flow, right? So dynamic mode decomposition of that and the resultant frequency of the primary dominant modes should give you the physics of the coupled system.
The problem is essentially that you know, the cell center information is moving to different places. So even if your mesh topologically doesn't change, like you know, cell 1 in the first snapshot will be here, and in the second snapshot it will be over here.
Yeah, but if a cylinder is oscillating, and for the amplitude and frequency region, if you get a reverse common wave, let's say, behind the cylinder, even if it's SR, the wave doesn't, the spatial temporal characteristics of the wave doesn't change, right? So it's a reverse common wave. So when you are taking snapshots, and if you interpolate within a window, let's say uniform,
yeah,
you can get
yeah. Or in this case, for example, you could also, you know, leave out the part of the domain that is actually changing, and then you can also do it. Yeah. Or if everything is moving, then it's also, I think, okay. So whenever you can do a change of reference frame, or you can mask the part that you don't need or that is complex, then you can use it in the same way. Yeah. Okay, so the first way of performing DMD I want to show you is based on sample planes extracted from the OpenFOAM simulation. And so I use a surface function object here. I sample P and U. And what you can do, for example, is take the surface values. That's also quite interesting. What I will show you is basically a plane, and is like a sample in the XY plane, which is at, you know, about this height, half of the cube. And so why is it nice to use sample data? First of all, because you don't get massive amount of data. You can quite easily work with that. And the second point is usually you need less physical time to find converged structures than when you have like three-dimensional flows or three-dimensional samples, let's say. Okay. And the tool I'm going to use for this analysis is FlowTorch, little Python library that basically facilitates loading the OpenFOAM surface data into your Python environment. So basically, it gives you access to the snapshot information and the fields. In this case, we are going to work with the velocity vector. Good first thing to do is to just look that you don't have any oddities. So you may just look at the temporal mean of the different velocity components. And then you actually create a data matrix. And you can see we first here, I hope this is large enough. We first extract the number of points and times. We allocate now a data matrix that has 3 times the number of points because we have X, Y, Z components, and that has as many columns as we have snapshot times. And then we fill this data matrix up using the velocity information. Now, one thing that you should do when computing any mode decomposition and your samples are not spatially uniform, then you should basically weight every entry in your state vector with the area if it's a sample plane, or with the volume if it's something volumetric. And this has some like theoretical background on how to compute how norms are actually defined, but it's also related simply intuitively speaking that you do not want to see an influence of your mesh in your analysis. So you don't want to have regions of high mesh density to pop up into in your analysis just because there is a large number of cells, right? Okay. And okay, I will skip over this. So one thing that I also like to do first is to actually compute the singular value decomposition of this snapshot matrix and to look at the singular values. And this is so the diagonal coefficients of the sigma matrix, if you want, if you go back to the material. And what you usually get is something like this for turbulent flows. So first, the importance of the modes decays quite quickly, and then it decays very, very slowly. Okay, which makes your life for the analysis a little bit harder than if you have a nice laminar flow. All right. Then you can also, what sometimes you sometimes find in literature to determine how large your PRD basis should be. You compute the cumulative values of your singular values, normalize them, and then you can, for example, in the case of the velocity vector forming the state vector, you can say, okay, I want to capture 90% of the kinetic energy in my flow, and this is basically reached when 90% of the when you have as many singular values summed up that you reach 90% of the overall sum. Okay, and it's not straightforward to see that this is actually related to kinetic energy, but you can work it out. That basically this gives you the content, or actually the square root of the kinetic energy. All right, then these are the POD modes. I will jump over them because we are already quite advanced in time. And you also see here, these are the coefficients associated with the different modes. And now one drawback, so to say, of the POD is that you can see some coherency in these structures, in these temporal signals, but they are not like isolated frequencies. So there's a mixed content of different frequencies. Okay, now we're getting to the DMD. And this is just, in this little Python library, it's just a single function call. You need the data matrix, the time step. And then what I usually do is to, perform an additional optimization of this B vector, which is like one of the most useful DMD extensions that exist. And what you get, as I mentioned before, from the DMD is very similar to an FFT. So you get a spectrum. Okay, and we can. So this is again this is very similar to an FFT. So we get the importance of individual modes over the frequencies, and now basically where we have peaks, those are important modes, dynamically important modes. Okay, and this dashed line, this is just the vortex shedding frequency that we isolated before in the force coefficients. But you see also there are some, frequency peaks here at 1.6. So the structure that or the frequency that we also observed in the probe data, for example. Now comes the great advantage of the DMD. You can actually now see what modes are associated with these frequencies, so which spatial structures. And first of all, okay, you have always a background node that is constant in time. And then you get, for example, here a mode, a peak at 1.5, so 0.15 hertz. This is vortex shedding. It might not be straightforward to see that right now, but you get used to interpreting the modes. And I will show you in a second how you can make the interpretation much more intuitive by, animating partial reconstructions of individual modes. And then you see here at this high frequency, 1.7 hertz, you see we have like small scale structures that are originating here at the front edges of the cube and that are propagating in the wake. Okay, as I mentioned, they are not so easy to understand. So what I usually do is to take the background mode plus the mode that interests you, and then to perform a reconstruction of the entire flow field just using these individual modes, and then to perform an animation of this partial reconstruction. You can find the code to do the animations here. And this is what I want to show you. So just to repeat, this is the original flow, the slice we were looking at. Now this is the low frequency mode that is basically associated to vortex shedding. And you see here, this is really in this turbulent flow, we actually have, embedded, let's say, the classical Van Karman vortex tree that we also find in the flow past the cylinder at Reynolds number 100, right? It's just like that the timescales are so different that with your eye, you will not, catch this structure by just looking at the flow field. And here it is also interesting. Here we have the mode at the high frequencies. And you see that this mode is associated to vortex shedding at the leading edges of the cube. And you see basically that also in the wake, you see these vortices still be present at the same. So you see changes of the flow field at the same frequency. Okay, now if I maybe go back again to this to give you a comparison. So what we were seeing, the high frequency mode, is stuff that goes on here, but that also is still present in the wake. Okay, now the time is almost over, but I still want to show you 1 second. Okay, how this is done in OpenFOAM. And to do that, I've actually created, I've actually created another case called full case DMD, which starts from where the preliminary analysis left off. Okay, and again, in the control dict, you find how to define the DMD function object. Now, what is currently still a little bit tricky in OpenFOAM is that if you do not want to perform DMD on the full flow field, but you want to select a subsection, you actually have to create a new mesh and then map from the original mesh to this, let's say it's called here coarse mesh, where the portion of the mesh where you actually want to perform the DMD on. So this is done using the map field function object. And then here you can apply the DMD, stDMD function object to one particular region, which is in this case called a coarse mesh. And you see here, this is the POD basis, the number of POD modes that you want. And you can, well, I think the rest is self-explanatory. So how often you want to sample, yes, to collect snapshots. All right. One final comment. Okay, I will show you another example of how to actually use DMD for compressible flows tomorrow morning at 10 in the aerodynamics 1 section. And we have a data-driven special interest group around OpenFOAM. And yeah, if you follow these links, you find all the information. There's also going to be special interest group meeting today in the afternoon at the same time slot as all the other special interest group meetings will take place. All right, and that's all I have for you today.